Hi everybody, this is Mechanical Engineering by Hand, and in this video I'll talk about pipe head loss, and we'll use the Darcy-Weisbach equation to calculate that. And that equation is shown here. It's head loss in feet is a friction factor times length times velocity squared divided by 2 diameter and gravity. And this equation can be used with all liquids, and it can also be used for gases up to a pressure loss of 40%. So let's look at this example. I have 300 GPM of water flowing into this 4-inch schedule pipe, and it's 100 feet long this way, and then it has a 10-foot jog down and back up. So there are 4 long radius elbows in here. So let me start with this equation. I like to estimate the size of the pipe. It's the diameter in inches is approximately GPM over 20, and then you take the square root of that. So this would be 300 over 20 square root equals 3.9 inches. So a 4-inch pipe would be a good start for this. And I'm going to, we're going to use this equation, but I'll calculate the friction factor last. So let's look at the length. There's 2 methods on the length, and one is to convert the fittings to an equivalent length of straight pipe. So the straight pipe itself would be 120 feet. That is this 100 plus 10 plus 10. And then we'll convert each elbow to an equivalent length of straight pipe. So we have 4 of those. And we can look up that equivalent length. I like to use this book, and in the appendix there is a table for that. These are all equivalent lengths for different fittings, and so we have a long radius elbow here, and we'll say that this is flanged steel pipe. So we'll look on this row and go over to 4-inch right there, and we have 4.2 feet for each elbow. So 4.2, and this equals 136.8 feet. Okay, now we need to calculate the velocity. So this 300 GPM converted to cubic feet per second is 0.668. The area of this pipe, which you can also look up in a table or calculate, is 0.0084 feet squared. And the ID of this pipe is 0.3355 feet. That can be looked up on a table also. Okay, so the velocity will be this cubic feet per second divided by the area, which is 7.56 feet per second. Okay, one last thing we need to do to look up the friction factor is calculate the Reynolds number. So that is diameter times velocity over the kinematic viscosity. So we have 0.3355 times 7.56, and then this, we'll just say this is water at room temperature, so that is 0.00001217, and that would be in feet squared per second. So this equals 200,000. So now we can look up the friction factor. I'll go back to this book again, and we look up the friction factor on a Moody chart, and those are found in lots of other books. This is the Moody chart in this book, and we have Reynolds number on the bottom, and then relative roughness on the right side. Relative roughness is just the specific roughness of this pipe divided by the diameter. So for new steel pipe, it's typically 0.0002 feet, and then you divide that by the 0.3355 feet, and you get about 0.0006. And you can see I just made some notes here. 4-inch pipe ends up being here, and then larger pipe is below and smaller pipe is above. So we'll just follow this 6th line over to a Reynolds number of 200K, which is right here, and they cross right there, which is right on the 0.02 line for the friction factor. And 0.02 is a real good estimate if you don't have the information, or if you don't want to go through these calculations. But if you want to dial it in, then you should probably look up the friction factor. So our friction factor equals 0.02. All right, now we have everything to calculate the head loss. So head loss in feet, 0.02 times our length times our velocity squared divided by 2g, which is 64.4, divided by the diameter, 3355, and that equals 7.24 feet, which for water is equal to 3.14 psi. So what this is telling us is, with a certain pressure at the beginning of this section of pipe, just simply through friction, it would lose 3.14 psi by the time it gets to the end. And this could actually be a plan view where the pipe is all at the same elevation, or it could be an elevation view where this pipe actually drops down 10 feet and then back up. That drop in elevation and then the same gain in elevation would cancel out, so you would just be left with the length of the pipe and the equivalent length of the fittings. So that's one method. Another method is to break out the fittings and use a K value. So let's look at that. K is F, friction factor of the fitting times its own equivalent length divided by D, and you can look this up. If you notice, we have F, L, and D, which are shown here, so we're left with V squared over 2G. So another way to write the head loss for this fitting would be K times V squared over 2G. Okay, so I'm going to look up the K value for these elbows, and I'll look in this book, and we have a table here, 90-degree bends, and this says R over D1, R over D2. For long radius elbows, that means R over D is 1.5, so I'll take an average of those two values, go over here to 4-inch pipe, and we have 0.34 and 0.2, so the average would be 0.27. All right. So K equals 0.27. All right, so now we can calculate the head loss for these 4 elbows. It's going to be 4 times our K value, 0.27, times our velocity, which is 7.56 squared over 2G, 64.4. And that equals 0.96 feet. And that is just for the 4 elbows. To to get the rest of the system, we need the head loss through the straight pipe. So we would go back to this equation. Head loss equals F.02 times the length, which is 120 feet. That is this 100 plus 10 plus 10 times the velocity squared divided by 2g divided by the diameter. Okay, and that equals 6.35 feet. Okay, so we have the head loss for the elbows and the pipe separately. So let me just add a note here. This is for the pipe, this is for the elbows, and this is for the pipe. So the total is going to be those two added up, 0.96 plus 6.35, and that equals 7.31 feet. So we can see this answer is a little different than this one, but they're reasonably close. Just depends on the information you get from the tables, but I would say that's good. They're close. So that is two methods for calculating head loss. We have this one where we look at the straight pipe and convert all the fittings to an equivalent length of straight pipe. And then this one looks at the straight pipe, and then we look up a K value for each fitting and add up the head loss. So hope you enjoyed that. Thank you.